that's
on the AOS one. I don't see why not. On the campus one, like the whatever the lines. I
got 331.
But on the UW-AOS.
All right.
That's if you put it up there. We're ready whenever Tristan is.
yeah.
All right. Well, thanks everybody for coming. It's great to see such a huge turnout here for the first, I think this is our first Colloquium of the year. Yeah, it would have been Labor Day last week. So it's my pleasure to introduce our speaker today, Ethan Nelson. Ethan was a PhD student in my group, so many of you who have been around for a while will remember Ethan. Ethan came in 2012. From Texas A&M University. He had worked there with a friend of mine, Anita Rapp, and she highly recommended we take him on, and so I did. And he did an excellent master's degree and PhD, wrote a number of papers working with my group on analysis of CloudSat observations.
I'll just put this up for you.
Yeah, some retrievals. I'm not going to do the whole story. Not going to do the whole story. But after leaving here, he did go to the Jet Propulsion Lab. I think he actually done an internship at the Jet Propulsion Lab and then decided to go and work there for a couple of years before then coming back and working at SSCC for a couple more years. And then after the pandemic, decided that he wanted to try his hand at working in the private sector, and apparently it's a good fit. Ethan is still there. I think he's working his way up. And you can go back to the title now because I'm just going to mention that, so Ethan now works for a satellite company called Tomorrow.io that's doing a lot of interesting work now in using small sats and their own proprietary software for incorporating satellite information to do better jobs of precipitation, maybe among other things. So Ethan is going to talk to you maybe a little bit about his career path and then a lot about what Tomorrow.io is up to nowadays.
Yeah, great. Thank you, Tristan. Can you hear me okay? Okay. All right, yeah, so it's been really a delight. Met with a few of you today, and I think there's some more meetings tomorrow. You can still sign up if you want, but it's been great to reconnect and kind of just talk about what we're doing at Tomorrow.io and kind of the future path forward. I've listed a few people here who I work with pretty often, but really there's a whole team of double-digit people behind the work that I'm going to be showing today that do really great things. So as Tristan introduced, I started at Texas A&M. If you're not familiar with my background, 2008. Worked with a few different people. Data assimilation, didn't like it. Satellite retrieval is pretty fun. Sheva Nasri, Anita Rapp. Came up here 2012. Actually, the spring break I visited, it was hotter in Madison in March than it was in Texas.
Yeah, 82 degrees or something.
Yeah, seeing people on the terrace was interesting. So that was a great dive into Wisconsin weather. Went to JPL for some time. Really got to know much more about satellite data and bureaucratic processes, if nothing else. Came back to Wisconsin for a little bit. Worked with Liam in the SIPs and also with Tristan on pre-fire, and then made that jump. Now I'm working with Joe, who I actually wanted to work with a postdoc for at some point. So it's kind of nice that I'm working with him, and then my 2-year-old now is also my other boss. So lots of fun times. So paths are never linear. Don't ever think that. The outline of today's talk, this hopefully comes from the abstract pretty directly. Just going to talk about a few different things. If you're looking for a really technical deep dive, this might not fully satisfy you, but hopefully you have a good understanding of some of the products we're generating, the satellites we've launched, and what we want to do going forward. So I'll start with this I'm calling Motivating a New Constellation. So if you're not familiar with Tomorrow.io, this is kind of our core product offering for business clients. We're really interested in providing the best weather information that our clients can use to make business decisions. So we have what we call this Weather and Climate Security Platform. This is an interactive data viewer, allows you to pull up a bunch of different weather data pieces, but also allows you to configure alerts and do really a whole variety of things. You're welcome to go to the website and sign up. I'll show that also at the end of the talk. But really what goes into this is a variety of things. So we have weather models. Those generate these layered forecast products that provide different sectors of information. So you can imagine some businesses might be more interested in one part than others. And then also these kind of user workflows. But I want to focus today on the weather models and what really goes into those. Obviously, we have a lot of observations that exist in the public sector from government agencies, satellites, weather models, weather observations. But we're really interested in trying to expand that footprint with our tomorrow.space, which is just kind of a marketing term, but our radar and sounders. These are just a few use cases I thought I'd throw up here for the types of things that businesses are using our platform for. So aviation, they can provide an alert. Do we need to start de-icing planes? Should we be delaying flights? Looking at mining. I like this one, on demand. Let's say you deliver umbrellas on demand and it starts raining. You're going to be expecting a higher demand for that. Looking more at sports platforms, knowing when to close the roof that might delay a game. Rain on a tennis court is never an ideal situation. And then also our government partners, we're also interested in providing both weather data and operations, but then also looking at more kind of applied use cases. So we partner with international governments through, it's called Tomorrow Now, which is our nonprofit arm, and one project we're doing is increasing crop yields for farmers by providing early notifications for when planting seasons are ideal. Okay, why is that not? Okay, so this is one example, right? Like if we're very quantitative, a weather forecast would say 12 degrees, mostly cloudy with a 40% chance of rain for New York City. But if you're not a meteorologist, that might not be super useful, or you're not able to do this at scale, right? If you have 1,000 convenience stores across the country and you're trying to digest information about what to do about those, this type of information isn't as useful versus setting up an alert. Okay, if you're a transportation agency, you might need to suspend rail service because of expected flooding. So ultimately, this is what our end users see, but all of this is powered by improved forecasts. So one problem, if you have any exposure to weather radar, is that it's not equally distributed globally in terms of coverage, or openness even for that matter. So CONUS, we're very blessed. We have the NextRad network. Europe also has a variety of consortiums, but ultimately that can come out of OPERA. And then some other countries have good radar coverage, but if you look at the map, there's a lot of dark spots on here where there's not good radar coverage. There's either no radars or that radar data might not be open or not properly running. So this is really the gap we're trying to solve with our space mission. And so filling that 90% gap, there was a statistic on there. So 10% of the globe is within reliable and accessible radar coverage, which means to fill that 90%, we need to use a different vantage point. Now, I'm at SSEC and SIMS, so satellites do exist. I'm not going to deny that. And we have quite a few that are up there. With geosatellites, right? We're very far away right now, optical and IR. I know GeoXO is coming in the future, so we'll have to revisit this slide at that point. But right now, we can really only see cloud tops. Can't really get good information about vertical structure, especially if you have a cloud there. And then when we're looking at the low Earth orbiting satellite missions, a lot of those are microwave, IR, GNSS-RO. They provide soundings and imagery, but either they might have a low combined revisit rate, so it takes them a long time to re-image a point in time, or there's just high latency. So, right, like GPM is obviously the thing that stands out with a radar, but we're looking at much higher latency on that data. So, not really useful when it comes to looking at short-term forecasting. All right. So as I mentioned, GPM, if you're not familiar, this is, so there's the Core Observatory that has dual band radar on it, but really it's a constellation of satellites, microwave imagers, that are really interested in trying to better understand precipitation globally and try to provide good coverage of that with good revisit. But as I mentioned, still, it's very expensive first off, and then also low revisit rate and also high latency on there. So we're really trying to take GPM and build on that sort of legacy. And so this is it. This is our planned constellation as we have it right now. So GPM, we've got the big core observatory with a satellite radar on there, dual frequency, and then I'll back out here. Microwave sounders, 8 to 11. But you're looking at many hours of latency for that kind of combined imager data set, and then for radar, it could be up to 3 days. So we want to try to improve that with tomorrow.AOS. So right now we're planning to have a constellation, and don't worry, I'm going to dive into much more of this in just a moment, but we're planning to have more than 4 radar satellites with a high swath and then quite a few sounders, which will hopefully provide sub-hourly data revisit rates and latency globally, both for the combined microwave imagers and the radars, and then also a few hours if you just take out the imagers and look at radar only. And then this tries to illustrate all these words I keep stumbling over between revisit rate, latency, and so on. This is, by the end of next year, so 2025, an animation of what our constellation would be providing from a microwave sounder perspective only, where we're showing just the data with up to an hour of coverage. So data is never more than an hour old on these images as we advance through time. So really good coverage globally, obviously over the poles because we have polar orbiters, but we're also looking at inclined orbits as well so that we can cut down those revisit rates in the tropics. Okay, instrument lineup. Any questions, burning questions so far? No, okay, great. All right. So the first one, so I've been talking about these radars. So this is going to be our operational radar. But first I'm going to touch on the Pathfinders, which we launched last year. So tomorrow R1 and R2, which were the first and second radars that we launched. This is just kind of a snapshot or rendering of what the satellite looks like. So we've got an 85 kilogram bus on there, high-speed downlink, which allows us to download full granules as we need them, decent power generation from solar panels. If you're really interested in antenna patterns and radiation patterns, there's a simulated plot there, a really nice beam. And then this just shows an image. So the radar is actually driven by, it's a software-defined radar, so it's driven by actually these digital units. So it's pretty cool to see those in actions instead of huge magnetrons, like they have at A&M, for example, in the building. And then just some stats there. So key point there, we have sub 5 kilometer footprint, orbit altitude 500 kilometers. In our duty cycle, we tend to average closer to 50 or 60%, but we're really not pushing above that. And then we're a Ka band. I don't think I mentioned that at this point. So that's great. And so these are actual, this is a picture of the actual 2 satellites post-assembly before they got shipped off for launch. And then we unfortunately didn't pay for first class, so there's no image of the actual satellite, but these were the points in time when they dropped. So you can imagine just a small little dot on the screen. And so these did launch at different times, which means they're pretty spaced out in terms of orbit. So then next up is the sounders. So we partnered with MIT Lincoln Lab to commercialize their microwave sounder technology. Some of you probably are familiar with the Tropics mission, so slightly modified instrument, but basically the same type of package there. We've got a 2,200 kilometer swath across, varying resolution depending on your frequency. And we picked it similar to Tropics, where we have 2 imaging channels, 7 that are really focused in the F band here, and for temperature sounding, and then we've also got 3 here in the water vapor absorption line. I have here the differences between Tropics and TMS. And so the center frequencies, like if you look at the actual frequency that the channel is focused on, they're the same. The difference here is that we're using dual sidebands instead of a single sideband. So we represent it with this instead of the other nomenclature. But basically the same channels, same type of instrument, slightly improved noise. Sorry, that took a while to get my coffee, but I found it. And then the sounding channels, and if you're very interested in radiative transfer, we get pretty decent vertical coverage. The dots here are our sounders versus the Tropics, which are the solid line. So by doing those dual sidebands, we get to move up the channels a little bit in the vertical distribution. And so these launched last month. If you aren't keeping up with space news, Here's a photo. This was released by SpaceX on Twitter, showing all the satellites. It's kind of cool to see these on the ride shares. So if you're not familiar, basically, some of these transporters, SpaceX launches up to like 60 smaller satellites onto the same payload into space, and then they release them over time. And so here they are, bolted to the assembly. And then one of them we got upgraded, though you can't see it. It's a very tiny dot. If you go back on the live stream, you'll be able to see it go down. And then the other one we were out of video coverage. So kind of cool to see these launched. And then lastly, coming soon, is our next generation full swath radars, which I don't have anything to say actually, but pretty much the same type of characteristics, just a full swath instead of a pencil beam. All right, no burning questions, so I'll keep moving. This is the first topic I really wanted to touch on that's, I think, kind of novel because it's not discussed often in the literature, and we're hoping to put it in the literature soon. But looking at mission operations. So as I previously mentioned, the duty cycle of the radar is on the order of 50 to 60%. So that means in a given orbit, we can't have the radar on for more than that percentage of the orbit. And that's really due to the smaller bus. We don't have a huge battery. We can't turn on that very power-hungry radar the whole time. So when it comes to mission operations, we have to decide when to turn on the radar. And so this is going to hopefully walk through kind of our strategy for doing that and being a little more intentional than just picking random times and random offsets. So I just explained all that. So these are kind of the three tiers of science tasking that we have right now. So really the first one is tropical storms, right? Like these are very impactful, very important, huge storms. So we're really interested anytime we can to cross over those. Next, we're also very interested in Cal-Val opportunities, so calibration validation opportunities. Since these are pathfinders, we're really interested on defining the instrument characteristics in space. So we can do lots of measurements, lots of calibration on ground. But when the payload's in space, things can change, though ideally not from an engineering perspective. So we want to match up collocations when we can with ground instruments. This was actually a nice partnership that Tomorrow Now did in East Africa. They installed 5 laser disdrometers that we're then using to make overpasses. So we're looking for the rainy season that's coming up in a few months. And then finally, we have this in the little detective there, just-in-time tasking, which I'll define here in a minute. And then this plot here. So if I have these colors that kind of match each tier, ideally we would fill up for every granule or every orbit as much as we can, starting with the red first, then orange and yellow, and so on. So the general process for tasking, one limitation, we might not always be able to contact a spacecraft, so we want to provide a long window. So generally we do a 48-hour orbit forecast, but we do that every time. And I'll talk about the extended times in a minute. But first off, for the tropical storms, we take our tropical storm forecasts, we constrain based on a certain off-nadir viewing. If you look really far at the storm, there's just lots of things that could go on. It might not even hit the ground, so then your attenuation estimates are going to be messed up. So we want to limit to off-nadir viewing angles that will provide good science data. Then we take those forecasts, find out where each of the eyes are or where they will be when our satellite's going in that vicinity. And then we derive those intercept angles. And then finally, we try to favor, not that this has come up much, but if we had like a bunch of different storms, we would try to favor the cyclones over, as opposed to kind of the tropical storms or the invests. Then once those are done, we look at the collocations. We pick our nowcasting product. If you've never heard that term, I'll define that in just a minute. We take the 0 to 6 hour time frame. We again do that limitation. And then basically for every observation site, we pick a 50-kilometer radius, and we say, if it's raining within that radius, it might not be directly over the site, but if it's raining within that radius, we want to task the satellite to go directly over the observation site. And really what we're trying to do here is account for potential errors in forecasting. So if I say when the satellite's going over that it's going to be raining 10 kilometers away but not over the site, I might have some sort of spatial error with that. So I'd rather just be safer than sorry. And if I get clear error returns, that's okay. And then lastly, this just-in-time tasking. So we're taking the nowcast again, we're limiting to the off-nadir viewing. But then what we're doing is we're actually saying, okay, based on our short-term forecast, which we're assuming has pretty good skill, can we find out where it's raining, or where we think it's going to be raining, and then can we try and intersect that in such a way that we provide the highest scientific value? And I call that this center of mass intercept. So I break that down. Okay, first the collocation. So this just kind of provides some spatial context for these collocation sites. So like I mentioned, these ground sensors we have, there are also some in the US DOE sites that we're looking at. We have our own ground cal sites in Bourne in Boston, or just southeast of Boston, and then also buoys. So one thing we do is we do these spotlight maneuvers over buoys to look at the surface reflectance, and then we can compare that against what the buoy measured in terms of wind and provide some sort of estimate for our reflectivity bias. And then the just-in-time is going to happen everywhere.
Is the radar antenna pointable?
It is, yeah. So, well, actually no, but the whole satellite. We're steering the whole satellite. Okay. Yep. And we're trying not to do anything along track. We're only doing across track, except for the spotlighting. We are doing both along and across to get that spotlight. Thank you for that clarification, Brad. Yeah. So this just-in-time. It's basically an image segmentation problem. So this is, you could Google canny image detection if you want. But really the basic idea is take these cells of precipitation and try and extract some sort of contiguous boundary around them and call these features. And then we can take all those features, plug them into a bag, and say, okay, which features are going to be the coolest, or most scientifically valid, or most useful. And what we're grading that right now is, right now, just to be the longest transect of high precipitation. Does that bias our measurements if you're trying to do this for climate studies? Potentially, but we're obviously open to multiple ideas. But this is kind of a first pass, really just to get a good understanding, especially as the radar is attenuating, how our precipitation algorithm is working. So this slide here, we have a nowcast. Our nowcast is fully global, but I slice up the nowcast to be where the orbit will be over the next hour or 3 hours or 6 hours. And then I take 5-minute chunks and I split up the nowcast to match those. So basically at any point in time, this is what the forecast would be when the satellite is going to be in that area. So time is actually varying spatially on this map, but hopefully that makes sense. And then this is just a schematic of the same type of thing. So if I'm the radar and I'm going along, okay, this is nadir, just pointing down. All right, I've identified 3 different cells I'm interested in, so I'm going to go ahead and turn and steer, go along there. Okay, I'm going to turn and steer, go along, and so on. And then this is where I'm trying to represent, we sometimes make trade-offs. You know, are you interested in 1 large cell versus 2 small? I don't know. I think every scientist will have their own opinion. So we're trying to do this somewhat subjectively. And so this is one example which isn't as attractive as I'd like it to be. But if you look at this coloring here, this is the beam incidence angle, so basically how offset the radar is. And this dark purple is 0. So if we weren't going to turn the radar at all, or the satellite at all, this is where the radar beam is, which is kind of right here. And then we've decided, oh, there's actually some precipitation here. So we steered the beam to then go this way and actually transect that precipitation, which maybe isn't as visible in the geo because I wanted to get the full path here, but you can see that we actually did intersect some precipitation. So it's pretty cool to see that in practice. And I'll note here, you're like, oh, well, why didn't you go over here? This goes back to what I was talking about, limiting the offset. So we can't be too far off nadir. And actually, both scientifically, and then there's also some licensing requirements. So we're obviously transmitting a radar in space. There are limitations with respect to that. So we do have multiple reasons to do that off nadir limit. So, summary slide, using forecasts to inform observations provides us with an optimal utilization of the radar with a somewhat constrained observing window and a constrained power budget. I would love to have the radar on all the time, but that can't happen. Now, when you start talking about multiple satellites, our R1 and R2, like I said, they launched at different dates, and they're far enough away, but when we start dealing with sounders that are going to have high revisit and be close in orbit, there's some trade-offs that come into play, right? Like, what's the value of an observation if you just went over that 10 minutes ago? If it's a slowly evolving storm, does that really matter? Does that matter for your data assimilation versus nowcasting? Is it the same sort of impact? It's a much more difficult problem, and really, like, by definition, a can of worms that we're slowly opening. So if anyone has any inputs, that would be a great opportunity. But next, I'm going to move into our satellite retrievals and nowcasting, and I think I'm okay on time here. So I'm going to do a 2-slide crash course in Bayesian versus neural network retrievals. So I hope you all bear with me. There's lots of nuance that I'm kind of sweeping under the rug here, but hopefully you get the basic idea. I didn't sub in that figure, so imagine that's kind of illustrative. But in the past, satellite retrievals have leveraged Bayesian methods to approximate a posteriori distributions. So basically, if we can leverage continuous or discrete estimates of what some sort of entity or distribution is beforehand, and map that to input parameters, then we can get an output. And so this is, Grant Petty did a paper a few years ago on information content, and I think this illustrates it somewhat nicely, if I can remember his exact definition, but basically you have like a 2D distribution here that talks about some parameter. So let's say this is the reflectivity of the cloud top on the x-axis, and then the y-axis is path integrated attenuation, which are conveniently things that I stole from my thesis. And then we'll say here on the kind of contour is rain rate, which these magnitudes are very much off, but hopefully this will help you understand. So without any information, if we don't provide any information to the retrieval, we just have this kind of understanding of the relationship. If the reflectivity of cloud top varies this way and PIR varies this way, we can try and get an idea of what the rain rate is. But now let's say we have an observation. Let's say we do know what the path integrated reflectivity is. Okay, now we have a different distribution. Rather than having this full spectrum, we've actually constrained that a priori distribution or prior into an a posteriori or posterior distribution. And so this plot just kind of shows that too. If you integrate across the y-axis here, this solid line shows what the distribution would be. And then once you've added this information of this one observation, you've actually changed your distribution pretty drastically. And so to build this retrieval, the scientist must select input parameters that will be used from the observations, and then they have to have some sort of understanding between the input parameters and the values you're retrieving. So people sometimes do this with a mathematical relationship. If you're doing just like channel differencing, and you can fit a line on that with field observations, or it might be some sort of forward model. Let's take a cloud resolving model, plug a radar simulator into that, and get those distributions. Or field campaigns, I guess those are kind of the same. So really this is about just shrinking this distribution space. Bayesian retrievals. Okay, neural networks now. I would posit that artificial neural networks operate in a similar manner. They attempt to construct a less straightforward but more robust mapping between that a priori and the posterior distribution. So to build a neural network, you must still select input parameters that will be used from the observations, and then somehow simulate, sample, or estimate the relationship between the input and the output. But now you also have to define a few other things, which these are, I don't really like the neuron analogy personally, but these are three what they call hyperparameters. So we have to define some hidden layers, neurons that compose that layer, and then some sort of transfer or activation function. If you don't understand any of this, that's okay because it's not completely relevant. But ultimately, the neural network is trying to use these hidden layers to refine those less straightforward relationships between the inputs and the outputs. And I would strongly recommend this paper by Simon Frunshu in 2018 from AMT, so it's open source. You can see the reviewer comments, which are great. He provides a great trial and error example of this hyperparameter selection. Really, this is just a bunch of secret sauce. Ultimately, we all have the same physical constraints. We have the same relationships. Ice particles aren't the same, or aren't different between the public sector and the private sector. We're just kind of tweaking some of these values. And hot take, ultimately, you can just think of a neural network as an ensemble of regressions. That's probably going to be as deep as I'm going to get today. So first going through the radar product, but it's important. The radar products. So we have what's pretty standard in the satellite radar community, the GeoProf algorithm. So this provides just some of the base level information, radar reflectivity, antenna pointing, geolocation, and then also information about the transmitter. So I mentioned this is a software-defined radar, which means we can change a lot of parameters. We're actually sending chirps, so we're slightly varying the frequency, and we can modify the actual center frequency that we're transmitting, which kind of helps us to reduce noise as we know which actual pulse power came back from. Then we have the L2A precip, so this is our first derived algorithm. And this schematic here does show the L2 algorithm. So we start with some basic geolocation, provide 3D lat and lon, which when we're not too far off nadir is pretty tidy. And we have some preprocessor. Then the first thing we do is bring in model data that provides environmental information that we can match with the radar. We derive an estimate of attenuation. Then we plug that into our neural network. And then the last step to be still implemented fully is an optimal estimation solver, which I'll talk about also. And then the third product is just an aux product, pretty standard again, collocated model data. It's actually pulled out as ancillary, which is slightly differently named. But this is much more useful for people who are interested, people like you all in the building, interested in weather and climate research, where you can really tie those radar observations to environmental information. So why use a neural network? That's a good question, Ethan. This is a schematic of the GPM DPR algorithm. So if you want to get, ultimately, if you want to get an understanding of where we're deriving the rainfall information, we have all these different components, right? We're estimating attenuation, we're estimating information about the drop size distribution, we're finding bright bands, and we're trying to classify the type. So there's a lot of moving components into all of this, ultimately to get your forward retrieval. So the idea is, and so one other point here, I'll back up. This is a dual frequency radar. So we're using KU and KA in GPM. So one issue is that the Tomorrow.io Pathfinder satellites are only KA band, so one frequency. So we're really limiting our information content to some extent by using only that single frequency, especially a frequency that attenuates in heavy rain or large hydrometeors. So the idea is, can we use information about the DSDs and the hydrometeors from the GPM data that's trained on dual frequency with microwave imager, and then can we basically pull out just the KA band? Like, can it learn all of these different nuances in the physical relationships with all of the information, and then can we just extract only the KA band and try to get some of that same information? So to do that, here's a slide on the neural network construction for those who have done this before. This provides just some of the information. So our training data, we're taking a full year of GPM level 2 data, so that includes the dual band radar as well as a microwave imager. We're calling that our truth. And we also include the incidence angle because that's a full swath. And then for the inputs of the algorithm, we're just taking the Ka band reflectivity profile, we're taking the freezing level, which we pull in from that ancillary or aux data set, and then our estimate of PIA. And the output that we get from that is precipitation rates at the surface, hydrometeor diameters, mixing ratio profiles, and then also these binary classification probabilities. So these come from GPM products, like is this convective or stratiform precipitation? Is it raining at the surface? Is there hail, and so on? And these are maybe the least well-defined, or at least well-behaving in the neural network, so we're still trying to refine those a little bit. But the process with training a neural network, we withhold some of our data, and we want to use that as validation. So I'm trying to display a few different things here, but if you look at the y-axis on the top row, the y-axis here is the estimate of the dual precipitation radar rainfall on the y-axis. And then on the second plot, this is if we include the GMI as well. And then as we move along the different columns, the x-axis corresponds to different products. So the x-axis over here is the Ka only GPM retrieval. This is the neural network trained on just the dual frequency radar. And then this is the neural network trained on the dual frequency radar and the microwave imager. And really, this is a lot to digest, but basically if you treat the y-axis as truth and the x is kind of your experiment, you can see if we look down here, we have a pretty high R² between our retrieval on the x-axis. So this is what our tomorrow.io sensor would be giving out as an answer to the neural network. And then the x-axis here is what our kind of gold standard truth is using a dual frequency radar and the microwave imager. So R² at 0.7, pretty good for a first pass. Let's see. Yeah, I think that's all I'm going to cover on that slide for now. Okay. Oh, yeah. All right, time's going. Okay, so the final thing, and this is a step we're still working on. Some people are very skeptical of neural networks, rightly so, in some regard, but what we're trying to do is actually implement a physical post-processor. So usually people will do a machine learning post-process to some sort of physical retrieval to minimize bias. What we want to do here is actually constrain the neural network with a physical model. So what we do is we take the hydrometeor profiles, so looking at the different particles that exist based on our neural network algorithm. We run that through a forward model and we simulate the reflectivity that it would see. And so there's going to be some difference because our retrieval might not be exact. And so then what we can do is iterate on that retrieved neural network until we get actually a much more in line plot here. So on the x-axis here, the blue line here is what the radar would see. The orange line is what the first pass of that forward model is. So we get a good structure, but it's not exactly matched. So then if we iterate, we actually improve our solution now by slightly perturbing that retrieval to get a reflectivity profile that's in line with what's observed. Obviously, there are lots of assumptions about forward model errors and so on this, but really trying to provide some physical grounding instead of just a neural network. Now some pretty images. Everyone likes eye candy. So hurricane season has been okay this year. These are a few overpasses of Hurricane Alberto as it moved through time. So this is the first pass, second overpass, third overpass. I don't know, it's just kind of cool. This was actually pretty close to before landfall. We get nice rain structure throughout, but I don't know, nothing super quantitative from these. Hurricane Debbie as well, landfall and kind of post-landfall. Actually some really cool, I like this. We have some anvil that's pretty heavy anvil actually that's overextending here to the north, and our retrieval actually picked up on some elevated ice particles, which for Ka band not always the case. And also correctly said there's not, that's not a rain signature. So pretty encouraging. And then lastly, Hurricane Ernesto, as it made its way, this is a very large map, but as it made its way across the Atlantic Ocean there. So yeah, great, we have data flowing. We obviously have some from last year, but I just wanted to show more recent examples. And then these are maybe not as flashy tropical cyclone, but even Southern Ocean, mid-Southern Ocean, we still get good precipitation retrievals. Again, good elevated ice still, I like seeing that. Same over here, all cold rain here. Yeah, pretty great. And then this just shows the collected files so far. So yeah, not much more to this. We're trying to expand this. We just weren't tasking really over the poles due to downlinks, but we're trying to expand that a little bit to get some polar observations. And then, of course, the Southern Atlantic anomaly. We've done a little tasking there, but trying to be cautious about protecting our satellite radar. Okay, great. So I've said a lot of stuff, but you want to know, okay, are you just pulling our leg? So we're also doing validation. This is an example of our level 2 validation. So we're co-locating NextRad. This is northern Minnesota, actually. So we're moving kind of into Canada there. Welcome, Tristan. But we have this nice cross-section showing up from the MRMS product. We have our collocated satellite radar, and we actually show pretty good agreement. The NextRad, or the MRMS product, drops off as we head for the north. But good that we're getting that attenuated rain structure is showing up in high rainfall rates over that area. So pretty cool. R squared of 0.83. All right. More robust validation. So looking at the top here, the L1C GeoProf. One thing radar scientists often do is compare the surface scattering off the ocean surface based on wind speed to see, because we can estimate that and see how close we are. So the GPM functions show up in these black and then black solid and dotted lines for different offsets. And then if you look at R1 here and R2 here, we actually have pretty good agreement based on wind speed here. So bias just based on these plots for R1 is 0.4 dB and R2 actually 0.1. So we're pretty pleased with this so far, but we're still taking measurements to refine that. And then the bottom half here is our L2 product validation. So taking one of those MRMS collocations and aggregating a bunch of those together, actually shows pretty good matchups here. So on the left here we have combining both our R1 and R2 radars against the MRMS data set, 0.86 correlation, which is great. We've got a nice distribution of lower precip rates, may not be exact everywhere, but we've got a pretty good one-to-one slope as well. And then on the right here, we're actually comparing just 1 month, but we actually compare the GPM single frequency product only to MRMS, and actually has a lower R value. Part of that comes from just the sensitivity. We have a more sensitive radar, so we can get lower rain rates. And then also, if you look at the one-to-one, it's actually slightly skewed. So we're trying to digest that a little bit more for the single frequency retrieval. But in any case, we're very satisfied with these results. So that's the radars. Sounders, sorry, this is a whirlwind of information. Sounders, I'm not going to spend too much time on this. We've got level 1 products, brightness temperatures, antenna temperatures, whatever you want, bias corrected, intercalibrated. We're also doing a regridded product and resampling. So as we pick these different frequencies of channels, they have a slightly different footprint on the ground. So we're actually playing around with regridding to a common footprint, which is important for like image recognition, image AI, machine learning algorithms, having all those on the same kind of footprint. So we're doing that, and then the level 2 products, again, this launched just last month, so we're still building these out. We've got a neural network a neural network retrieval for atmospheric temperature and water vapor profiles. We're hoping to use mirrors, which if you're familiar with other microwave sounders, is kind of a product with a long legacy. We want to provide a similar product to match that record. And we've also got a precipitation retrieval and hopefully in the future, a tropical cyclone intensity estimate, which probably won't be ready until next season. Again, for those who are familiar with neural networks and interested, so our training data, what we do here with pre-launch, we're using, so this diamond run is a very high resolution global simulation. I'll have a slide on it in data simulation. But we basically run a radiative transfer model on that to simulate radiances of our sensors. We use that as our training data. And then we provide all the brightness temperatures, the sensor zenith angle, and also land fraction, just to get some kind of contrast between ocean and land. And then we spit out a bunch of information about thermodynamics, temperature, water vapor, IWP, surface temperature, surface precip rate. I had to add these to disclaim that I got to show these. But these are from Typhoon Yagi, which is actually the more recent case, and then also Typhoon Shanshan. And so this GIF actually, or GIF, shows 3 tropics overpasses, and then the last one is actually TMS. So if you stare at the eye, they actually look pretty similar, which is great. But we've got a lot to do now in terms of building out those level 2 products and really getting those operational. So great, we have a bunch of data. Now how do we use it for our customers? If we go back to that kind of first slide of translating forecast data into actionable insights, how do we actually improve that forecast data first? So I'm just going to fly through these slides. This is the current state. So if you go on our platform, this is what the real-time precipitation looks like. We have a nice global product. It's contiguous along, or we provide nice boundaries between ground radar sites like I showed, where we have over CONUS, but then also in oceanic areas. But real-time precipitation's not often enough. I mean, we're obviously meteorologists, we want to forecast. So how can we kind of make this better and provide information for the future? Depending on how far you're looking, you might need different models. So nowcasting, I mentioned this earlier. If you're not familiar, is just a fancy term for short-term forecasts using some sort of observations, and using those observations much more directly than you would in data assimilation. Then you move to short-term, medium range, and so on. So I'm going to focus on nowcast first. There's a lot of news, lots of press releases, articles on every news site about generative AI, improving forecast models. If you came for that, I don't have any today, other than just to show you that it's happening, and that's great. Traditionally, if you want to take these radar observations now and push them into the future, you use something like optical flow or some sort of image technique to really propagate that image forward. You maybe have some environmental information about derived wind speeds or some ancillary data, but ultimately if you just have a few sequential time steps, that'll provide enough information to give you a sort of decent nowcast forecast. But generative AI is saying, let's just throw the kitchen sink at it and do these really complex techniques, which is great. But the problem is you got to have ground observations. You got to have really good radar observations to be able to propagate this forward. But as I stated at the intro, most of the globe does not have ground radar. And so precipitation nowcasting becomes a fundamentally different problem in these regions. The standard really has been iMerge, or kind of this GPM constellation. So combining infrared radiation, IR measurements, microwave imager estimates. There's PDIR as an algorithm, like from Irvine, for example. So really trying to provide global information from that GPM constellation. That works great, but the problem is it has really high latency because they got to bring in all that data, they got to do some corrections to it. So not super good for forecasting. And now if I have on this plot here, the x-axis here is time. So we're starting at time equals 0 on the far left, and then we're going out to 3 hours. Y-axis here is Heidecke skill score. So basically the probability of how well you forecast events occurring, so precipitation being at least a quarter millimeter an hour versus what actually happened. So these dots here are just the HERS. So if you take the high resolution rapid refresh NOAA model, that's your skill score. So this can kind of be your baseline for what do you do if you just plug in an NWP solution for short-term forecasts. All right. Now, if you take iMerge, you actually do get an increase in skill. So it's hard to define these like very quantitatively, but I mean, you do see an increase in skill all the way up past 2 hours. But again, like I mentioned, this has a high latency. So now what we're doing is saying, okay, what if we take a satellite-based nowcast? So what if we use our global precipitation retrieval and propagate that in time, which has a low latency because we're always generating a real-time precipitation image. We actually have higher skill all the way out to almost 3 hours. And then finally, this radar-based nowcast. So what if we now start plugging in our satellite radars? What if we plug in all the observational radars we have from the ground, and also our other constellation data? We have a much higher skill score that then does decay as we move out. So some improvement there, which is great.
Ethan, were those all generative AI forecasts with?
That's a good question. This was 50 case studies, so I don't know that there's exactly a generative AI, but this GIF might show some estimates. So this is the evolution over time from MRMS. This is using nowcast.net, which is one of the models. So this is the bias, or the difference between the two. And so yeah, it does a good job of capturing the feature, but again, you got to have that MRMS data to really run that. So we're really interested in providing data that can eventually go into those types of models. So our next generation nowcasting, we're exploring time-resolved neural networks with a flexible inference to drive our next generation nowcasting. So again, going back to that initial kind of image of the real time, this is just our ground radars, but then we can plug that in with satellite data to provide a nice gap filling. And then finally, this plot here just shows, okay, now what if we take our ground observations, but also plug in if we have a microwave imager overpass go over. And so we can see that we can change some of the precipitation that's going on over here. and also provide context across this large swath. Again, this is very like fresh right now, so I don't have any good quantitative results, but something we're really thinking about. And then this is an example using our full sounder constellation against a simulated, or I mean, it's a typhoon that hit, but simulating the typhoon reflectivities hitting Japan here. And so this plot here just shows the accumulated rainfall over time across the domain. So again, kind of that I-merge, which is great, but on a high latency. Here's in the red. Green is our current nowcast, which has some improvement. But as we move towards next generation, actually without using ground radars, we actually do a good job of matching the skill of just ground radars only. Okay, and finally, because I know we're almost at time, so OSSIs, we're also running OSSIs to figure out how to simulate these into longer term forecasts. So we're using this Diamond 3-kilometer run, running a forward model on those to simulate radar reflectivities. Then we use a control of this UFS model where we're plugging in and we're denying and adding observations. And really, I mean, the take-home point here is just change in the RMS on the x-axis. Y-axis is the pressure as you go up in the atmosphere. But we see when we start to add in even 2 microwave sounders in the dotted blue or purple, and then the dotted gray as well, we're actually decreasing our RMS, which I mean you'd expect as we get more information about the atmosphere, we expect to have lower errors. Okay, and then finally, S to S to climate. I have a big question mark here because this is where we really rely on academic partners. So if you've got ideas, be thinking about them. That's great. Ideas that we can use this data. I mean, obviously we can evaluate climate model distributions, but there's a lot more nuance there and other ideas. So path forward, covering this again, plan constellation. Already seen that slide, so it's repeat information. We can go back and look at the recording, same there. This is our launch timeline. By the end of, well, so we've got here on the radars, Pathfinders, this was the 2 I talked about. We launched those last year. Those have been going on okay. We're developing our next generation, going to be launching those, not this year, but following. And then sounders, we've already launched 2, and we've got a lot more to come with a much faster timeline. So data, what about the data? We're actively pursuing opportunities to provide data through government agencies. I can't say it officially, but you can Google agencies and our company name, and you might come across a press release from Friday. If you have a relationship with programmatic management, be sure to indicate you're interested, but we're also interested in partnerships always. You can also go to this. This is our like landing page for actual satellite data as we release it. So you're welcome to go there. Otherwise, feel free to go to the website, plug in there. We have a cool little API if you like playing around with Python or other libraries. I don't know, you can have an updating weather forecast in your kitchen, something like that. So with that, I'll take any questions. Thank you.
Any questions for Ethan?
I think that'd be your record for slides in a presentation.
Yes.
It's close.
About 69.
I was going to say, I disapprove, but we'll talk about that after. Let's start with early career researchers first and students. Any questions?
Hey Ethan, good job. I have a quick question about the satellites you are developing. Can you tell us about what is a typical lifetime of any of these launches and maintenance issues, or like the operational side?
Yeah, that's a good question. I don't have hard numbers, but 2 to 5 years I think is generally an estimated lifespan for industry standard. Obviously that's like an idealized number. Could be higher, could be lower. But I mean, we're already thinking about next generations of constellations. So we've got this development plan for the instruments that we've already designed and want to launch and have our ride shares booked. So there are more iterations to come, even if something were to happen with some of the satellites. And then your other question, if you could repeat that, because I think I had an answer.
Like what are the maintenance issues?
Oh, maintenance issues, yes. Yeah, I don't know. This is kind of my first exposure actually to like instrument commissioning and satellites, so I might have like a very skeptical view. But you know, obviously there's always issues potentially with ground systems, with contacts. I mean, we're dealing with much smaller satellites, so it's not as easy to contact them. Not that we were like having issues with that, but there's always a risk for that. you know, the satellites, there's not really a nice, if they're so small, there's not a nice propulsion system, so they're slowly decaying over time. So that's obviously another issue. If you have solar winds and flares, that can be changing orbits. So I'm definitely not a rocket scientist by those means, but yeah, there's always just, yeah, what do the rail car agencies say? Like wear and tear. Wear and tear happens. Or your rental.
Tropics Pathfinder lasted 2 years.
Okay, 2
And
years.
that was a test unit, so, you know, just to give you an idea.
Yeah, and to be clear, our Pathfinders are tests. We're not expecting 10 years out of them. They're not going to be like the next cutting edge operational system. But they were the first example of our SDRs in space, so that means it works great. We're learning a lot of lessons on its tasking and so on.
Yeah, go ahead.
2 questions. First being, could you comment on where those attenuation estimates are coming from? Is that from Bayesian estimation?
You mean like for our satellite?
Yeah.
So we look basically just at, so like, I guess I can show an example here. If you look at just a granule, wow, these are a lot of slides. So if you look at a granule here, like we start here and we say, okay, what's the reflectance from here? And then we basically look at the difference as we go along. And providing, you know, some, I don't know the correct term, but we're providing some corrections, yes, as well.
And then my second question was for your neural network for the radars. Has there been any discussion on adding more inputs, or have you kind of maxed out the skill in terms of what you can input?
Yeah, I mean, the radar development has actually been kind of a backseat at this point with the sounders, but I mean, I'm definitely interested in adding more information, right? Like this is pretty generic. If you plugged in latitude, right? There's a lot of information there, for example. So we're definitely interested in expanding. This has been our first pass, and we're definitely hoping to improve that. Same thing with the sounders. Elevation is a good example. That's obviously going to change your skin temperature.
Okay, go over to anything now, Brad?
I really like the idea of combining the neural net as a first guess for the optimal estimation. I think that's a really nice balance. How expensive though? I mean, you are advocating low latency. The optimal estimation must be quite the same.
Yeah, it's ongoing development. So part of that is speeding up the process. Yeah, for sure. So right now our operational algorithm is a neural network. But our hope is, if nothing else, to have a year data record where we can actually look at the correction that's coming from the optimal estimation and try to improve the algorithm, the neural network algorithm to begin with, so that we don't have that bias. So this will be, probably what this will be is more kind of the iMerge equivalent, like research grade product that comes out on a delay. It's not cheap for sure, especially compared to a neural network inference, which is lightning fast.
Tim, did you still have a question? Sorry.
No,
Okay. No, it's the same one. Yeah.
And the other point, like, I guess as a personal point, I mean, I don't believe that I don't delude myself that neural networks are an end all be all, because there has to. First off, we're building it on a physical retrieval, so that's important. But I do think grounding it in physics in some way is important. Yeah.
Would you see these products being incorporated into iMerge at some point in the future to be like the community's basic case of precipitation net?
Yeah, we actually haven't talked about that, surprisingly. But yeah, I think that could be a good avenue, because ultimately we can provide similar information. Yeah, we definitely need some sort of data record to really ground our validation or biases. But yeah, that's a good point. I don't know why we haven't mentioned that internally.
You need another one?
Yeah, sure.
When the full constellation is done, what is the estimated lead or lag time of each radar and sounder? I don't know if I saw that.
By lag time, do you mean like so, I don't know, I think it's on the animation slide. We're hoping for sub 30 minutes. Sub 30 minutes globally, which I don't know if that GIF was
It's in the early slides.
Yeah, oh, it was real up there. And at the end, but I was already too far forward. Yeah, so if this shows just observations an hour old, I mean, you can stare at a spot, and this is a 5-minute time step, and there's a flash there pretty often. I mean, I should point to the poles, because those are the lowest, but we're going to be we're launching some. I mean, right now we're just in polar orbiting. We're going to be launching some in an inclined orbit so that we can really decrease those revisit rates over the tropics. So we have a good kind of mix.
So then will your products incorporate previous overpasses in their neural network? Is that?
Yep, as long as we have that data downlinked, yeah, which kind of gets at that. I guess for the sounders, that's maybe not as much of a consideration because the sounders are always observing. But you know, when you think about having a low latency constellation, you have ground stations across the globe, and so you do have to weigh, like, is it better to downlink and not observe over here, or should I re-observe this position that some other satellite in another orbit saw, and then save that downlink? We're trying to figure out how important that is on the forecast. It obviously depends on the type of convection. Tropical cycle in 20 minutes probably isn't going to change much.
All right, one last question, I think.
Okay, then I'll save my fun question. I'll save asking my detailed question about the boundary later. I was going to ask you, if on behalf of the students, as somebody who came out of this program and somebody working in this industry, what is something you didn't learn during your time here that's been essential to be able to be successful here?
That's, yeah. Ironically, what half of the presentation was, which is machine learning.
Yeah.
You know, and sitting on interview committees, I think having some sort, for the private sector, having some sort of exposure, I think is very, you don't have to like be running your own NVIDIA model, but like knowing what PyTorch is, or like having an understanding of gradient boosts or neural networks, like just knowing what that is, I think gets you at least above 50% of the people behind. Which is, I mean, that's not any fault of the department by any means. Obviously, this is very quickly evolving.
Very good.
Yeah.
And I've heard rumors there's already one class it's
So
being touched on. So, yeah, I mean, I would continue to advocate for that, I think. Yeah.
All right, great. Join me in thanking Ethan one more time. I will add on behalf of Ethan, I hope this is not overstepping my bounds, but Ethan is in town, and so I think that if anybody wants to follow up with Ethan, you know, down the road, he would probably be more than happy to hear from you and, you know, talk a little bit more offline. So even though he's done and this is his only day here.
Business cards?
Yeah, he's got business cards.
Swag. I don't
Contact
have
him.
swag, I'm sorry.
Ask more questions. Thanks a lot, Ethan.
Yeah, thank you.
all right.